by Ella Hilbrecht. Saponification is the reaction of a triglyceride with a sodium hydroxide or strong base, resulting in a glycerol and then a soap molecule. In this case, the example here is for olive oil. Cold process soap reaction. So we're going to be mixing sodium hydroxide with water to have a full dissociation, since sodium hydroxide is a strong base. This will result in an exothermic reaction. This solution will then be placed in an ice bath to cool. Oils will be mixed separately and heated before being added to the sodium hydroxide solution, and this will be the start of our saponification reaction. Sodium hydroxide and water solution will be mixed with coconut oil and olive oil to start the saponification reaction. Stir until trace, so that means enough soap molecules have formed to create a milky color and texture to begin to occur on the surface of the solution. At that point, once we're after trace, we're going to add in colorants and fragrance before mixing it into our mold. The cure time for the soap is 6 to 8 weeks to fully harden and for the water to evaporate off. How does this occur? Hydroxide ions from NaOH attack the carbonyl group in the ester linkage of the triglyceride, initiating the reaction. This reaction leads to the formation of an intermediate, which then collapses, resulting in the formation of a molecule and glycerol. In the case of olive oil and coconut oils, the specific fatty acids released would depend on the representative compositions. For instance, olive oil is rich in oleic acid, while coconut oil contains high amounts of lauric acid. So the importance of this. Soap molecules have a hydrophilic head and a hydrophobic tail. So what's going to happen is when you introduce them to fats or any kind of oil, they're going to surround it and create a micelle, where you can then use a soap to wash the oil away. This is important for hygiene, household cleaning, laundry, and then medical uses, so just keeping clean. Kinetics. The saponification reaction is second order, meaning its rate depends on the concentration of both ester, fat or oil, and the base, like sodium hydroxide, used for their reaction. Commonly, the rate of saponification increases with temperature. Equilibrium. So, theoretically it is reversible, but practically it's really not. The reaction heavily favors products, and the KEQ will be extremely large. Sodium hydroxide is a strong base that dissociates completely in water to produce hydroxide ions. These hydroxide ions act as nucleophiles, attacking the carbonyl group of the ester group in the triglyceride, initiating the saponification process. The ester group in the fat or oil is slightly acidic and able to react with the hydroxide ions. The reaction between the ester and the hydroxide ion leads to the formation of soap, or otherwise known as the salt of the fatty acid, and glycerol. Although the reaction between the fatty acid ester and the base is essentially an acid-base neutralization reaction, it's driven towards the product side due to the complete dissociation of NaOH in water and the stability of the soap and the glycerol products. pH. As sodium hydroxide mixed with water dissociates completely into an Na and OH cation and anion, the pH will be above 13 for the solution. Once that's added to the oils, it will start our saponification reaction, where the pH will decrease as both the OH and Na are consumed and the fatty acids are cleaved from the triglycerides. pH of the soap will decrease with time when curing as well, which is where we allow the water to evaporate off, but a usable soap is usually between the pHs of about 8 to 10